All right, welcome back, Physics C students, to Work Energy Power Notebook Video 2. We're going to start off by looking at the definition of work a little closer. Work is defined to be, remember the triple equal sign means defined. Work is defined to be the integral from A to B of force dot product with a tiny little element dr, and dr is along the path that the object is moving in. And this is a path or a line integral. We can simplify this a bit. First, we'll start by simplifying the dot product. And when we do that, we'll get work is equal to the integral from A to B of the magnitude of the force times the little element dr, the magnitude of it, we're not including direction here, times cosine of theta. Theta is the angle between F and dr. And if the force is constant and theta does not change, that means the angle between the force and the path of motion doesn't change. If that angle is constant, then we have that the work done is equal to the force, which can come outside of the integral as a constant. Cosine of theta can also come outside of the integral as a constant. And we're left with the integral from A to B of dr. And when you integrate dr, that just gives you the distance that you moved along that path. And this is the formula f d cosine theta, where theta is the angle between the force and the displacement. That's the formula that you would have learned in Physics 1. Now, up in the corner here, I've got 4 boxes, and we're going to go over 4 different situations where work is positive, negative, or 0. So first we have no work if the force is 0 or if our displacement is 0. And delta x here, we could think of that as a d. If there's no force or no displacement, you have work. We will have positive work done on an object or on a system if 0 is less than or equal to theta is less than 90. It can't be equal to 90. It could be equal to 0. This would look like maybe an object that is moving to the right. The force could be up at an angle like this. And as long as that's an acute angle, cosine of theta will be positive. This gives us a positive amount of work, and that is symbolic of energy being transferred into the object or into the system. If theta equals 90 degrees, we also have no work. Cosine of 90 is 0. So if we were exerting a force upwards and the motion was to the right, 90 degrees, no work being done. We get negative work if we have an obtuse angle where 90 degrees is less than theta, less than or equal to 180. So if we are moving to the right, but our force is directed like somewhat in the opposite direction, the left or up and to the left, then we get a negative amount of work done. All right, let's take a look at different types of energy. The 2 main types of energy that we'll focus on in this class are potential energy, which is energy that's stored up and ready to be released under the right conditions. It is It has to involve a conservative force. We'll talk more about that in a moment. And the other main type of energy we'll focus on is kinetic energy. That's energy associated with motion. Remember, kinetic energy is somewhat relative because it depends on your frame of reference. Overall, there's many different types of energy. We have sound, which is kind of like vibrational energy of the air. So in some ways it's kinetic, but we have a special name for it. We have thermal energy, heat. That's also kinetic energy, but it's on a molecular level. We have radiative energy, light. Not only light, but X-rays, gamma rays, infrared, microwaves, radio waves. All of those are forms of electromagnetic radiation. They can transfer energy. The forms that we'll focus on in this class are what we call mechanical energy, which have various types of potential energy, including atomic or nuclear. There's energy stored up in the nucleus of atoms, be released under the right conditions. Chemical energy, which is really electromagnetic, that's energy stored up in bonds. Gravitational energy is stored up in a positional relationship between the Earth or between any two objects that have mass. We have electromagnetic energy, which is energy that's stored up between charged particles. And elastic energy, energy that would be stored up in a spring. So we could also say elastic or spring. And elastic and spring energy is really electromagnetic again, because in a spring, the bonds in the metal are at a certain angle. When you compress or stretch the spring, you're changing the angle between the bonds. Now, if you push or pull too hard, you can permanently deform the spring, but within limits, if you just distort them a little bit, they will want to bounce back to their original positions. So in Physics C, we cover mechanical energy, including potential energy, gravitational, electromagnetic, which we'll get to next semester, spring, and we cover two types of kinetic energy: linear, where the center of mass is translating, and rotational, where the object is like rotating around its center of mass or some other point. And those are the types that are covered in Physics C. Now, a few notes on power. Power is the rate at which energy is transferred or the rate at which work is done. Both of those statements are equivalent. The average power is the change in work over the change in time, which could also be described as the change in energy over the change in time, since work is a transfer of energy. Our instantaneous power takes the deltas and turns them into derivatives. So dW dt, the time rate of change of work, or the time rate of change of energy. And we're going to derive an equation now that's not on the equation sheet. I'm not sure why they didn't include this one, but it's on the it's useful to know, and here's a quick little derivation for it. We're going to start with power is dW dt, the time rate of change of work, and that is going to be d dt, and then for work we have the integral from a to b of f dot dr. Now this integral is a integral along a position. This derivative is a time derivative. They don't have anything to do with each other. They're not going to like undo one another or anything like that. And if f and theta are constant, then we can simplify that dot product. Remember, that becomes fd cosine theta. So we have d dt of fd cosine theta. The force is constant and cosine is constant. So that means we're left with the integral or the derivative of dt, and that's like dx dt. It's the derivative of like your position with respect to time, and that is velocity. So this becomes f v cosine theta, force times velocity times cosine of the angle between. If it makes this easier, you could replace that d with an x, right? Distance x, same kind of thing. That might make it a little easier for you to see that d dt, dx dt becomes velocity. Okay, on to the next page. Conservative and non-conservative forces. What are they? How do we tell the difference? I wish I had actually put these stickers in the reverse order, because I think conservative forces are a little bit maybe easier to understand, or at least easier to discuss first. One way of defining a conservative force, and note my little typo there, there's a couple others that have snuck in along the way here or there, but for a conservative force, the work for a closed loop, and a closed loop has a special integral sign. It's like that. If you look at your E&M equation sheet, you'll see those a few times. We will deal more with these next semester. But a closed loop integral of f dr for a conservative force, that will equal 0. That means if I started right here and I did some kind of a loop, now it doesn't have to be a circle, it could be any shape. I could do a rectangle. As long as I get back to where I started from, that's a closed loop. The shape of the loop doesn't matter. If I go around that path and I do no work in total, then I have a conservative force. If you think about gravity, as I go higher, I'm kind of increasing all the work that gravity does on the way up, gravity does the opposite of it on the way down, and then you'd get back to where you started and you'd have the same amount of energy. Basically, all the work that gravity does in one direction, gravity undoes it in the other direction. This is not necessarily true for non-conservative forces. For non-conservative forces, one of their defining characteristics is that the work around a closed loop or a closed path of the force dot product with a little path element dr, this will not equal 0. If I start here, again, it doesn't have to be a circle, but I go around the loop. When I get back to my starting spot, the work done by a non-conservative force will not be 0. Take friction as an example. If I go along here, friction is always opposite my direction of motion, and friction does work the entire way. Friction is always doing negative work. It's always taking energy away. If you think about gravity, if I was going in a vertical circle here, on the way up, gravity pulls down. So on the way up, gravity does negative work. But on the way down, gravity does positive work. So those would kind of cancel each other out. Unlike friction, which is always doing negative work the whole way around. Now, there are some more complicated ways of defining conservative and non-conservative forces that involve taking partial derivatives of components of your force in certain directions, but all that gets way beyond the scope of what we need to cover in this class. Another way of defining or thinking about conservative, non-conservative forces, instead of a closed loop, if you just went along a path from one location to another, let's say that we start at position A, and I've got position B over here, and I take path number 1, and then I take some other path, we'll call that number 2. For a conservative force, the work for path 1 will equal the work for path 2, whereas with a non-conservative force, the work for path 1 will not equal the work for path 2. So what are some examples of these types of forces? Well, for a conservative force, there's only a few of them. Gravity, spring, or elastic, and electric. Those are the three types of forces that will have potential energy associated with them. In this class, those are the only three conservative forces we look at. So if there's any other force, it is non-conservative. Common examples of non-conservative forces, this is not an exhaustive list, but common examples would include friction, drag, an applied force, a normal force, tension. Now, just because a non-conservative force is present doesn't mean that it necessarily does work. But if it does work, the work will depend on the path that it takes. Same thing with conservative forces. Just because they're present doesn't mean that they do work, but if they do work, it will be independent of the path taken. All right, this leads us to that big idea that James Joule came upon, conservation of energy. The idea that energy is not created or destroyed, it just changes forms and gets transferred between objects as they interact with each other. When objects interact, they do so by exerting forces, and we know Newton's third law says forces are equal and opposite in direction between the two objects. And so one object, if they exert a force over a distance, one of the objects is going to have positive work done on it. The other object is going to have negative work done on it because it's the same magnitude of force and the same distance. The positive work done on one object would be equal to and opposite to the negative work done on the other. The amount of energy that one object gains is equal to the amount of energy that the other object loses, so the total amount of energy never changes. Now that's true really of all forms of energy, but in our class we're going to look at mechanical energy specifically, which doesn't include energy that's being lost, like sound and heat or radiated out. So for mechanical energy, it's the sum of potential and kinetic energies, the types that we listed on the previous page. And for a group of objects, the sum of mechanical energy will not change unless work is done by a non-conservative force, any non-conservative force, internal or external, or if work is done by a conservative force that's outside the system, an external force. So any external force doing work will change the energy. And internal forces, if they're conservative, they just transfer energy between potential and kinetic. Internal forces that are non-conservative will always change the energy of the system. And this is a conservation of energy equation. The change in kinetic plus the change in potential, and this is all the different types of potential energy, is equal to the work done by external or non-conservative forces. Right? Work done on a system by any forces external to the system, doesn't matter, any force, conservative or non-conservative, or non-conservative forces that are internal or external. So any external force, any non-conservative force, whether it's internal or external, will always change the energy of the system. And just a couple more notes to make on out. Potential energy here, if you include gravitational energy, spring energy, or electric energy, then you're implying that those the things that create those types of energies are part of the system. So the associated objects are part of the system. So if you include a source of potential energy, you are implying that the object associated with that potential energy is part of the system. If I include gravitational energy, I am saying that the Earth is part of my system. And here we should note that friction or drag they always are going to do work. They'll always change the energy. And when I say friction, I mean really kinetic. Static friction can change the energy. It depends, but kinetic friction always will. If we have tension, an applied force, normal force, or anything else, only if they do work. Tension won't always do work. In a pendulum, tension is perpendicular to motion. Tension is towards the pivot point, but the motion is radial. So tension doesn't do any work in a pendulum, and it won't change the energy of a pendulum. But if you pull a box across the ground with a rope, then the tension is in the direction of motion, and tension definitely does work, and it will change the energy of the box. And lastly, we can say spring, gravity, only change energy of system if they are external. And if they're external, then you do not include them as sources of potential energy. All right, that's going to wrap it up. Hope you have a good day or morning or evening or whatever it is, and look forward to seeing you soon. Bye.